Now, in this part of the lecture, we're going to talk about the Heaviside step function, which is a special function used when we're modelling processes that switch on and off. So in the rest of this class, we're going to talk about the step function or the Heaviside step function. Now, the presentation is centred around Laplace transforms, but even if you don't know anything about Laplace transforms, you'll still get some interest, I believe, out of this presentation. Okay, what is the Heaviside function? Well, it's a step function that's defined in this way. Well, it's 0 for t less than 0, half here, and 1 for t greater than 0. So if I draw a little picture, so to the left of 0, the value's 0. To the right of 0, the value's 1. And at 0, this particular definition says that the value of the Heaviside step function is 1/2. Now, you may have seen different definitions. Don't worry too much about how it's defined at the jump point. Okay, now different textbooks define it different ways. Sometimes they don't even define it at the origin. Okay, sometimes they define it to be 1. Sometimes they define it to be 0. It doesn't change any of the important aspects that we'll look at. Okay, so you can sort of think of this as the average of the jump, if you like. Now, hopefully you can see why it's named the step function, because the profile looks like a step. Now, a slightly more general function is the shifted version of the Heaviside step function. So essentially, here a is some non-negative constant. You just take this curve and you shift it a units to the right. Okay, so if I wanted to do a quick sketch there, t. Okay, so essentially it's the same behaviour, just shifted a units to the right. Okay, well, we're looking at the we will look at the step function in terms of the environment of Laplace transform. So let's calculate the Laplace transform of this function and see what we get. If we just quickly refer back to our table, so here's the step function here. They've used a c instead of an a. They claim that the Laplace transform of the unit step function is this. Okay, so let's just see how that works. Before we do that, let me just motivate the step function a little bit more. It's a typical function used in many areas of applied maths to model phenomena that are switched on and off. And like I said before, do not be too worried about the value of the step function at the point of discontinuity. We're going to use this convention. Okay, so let's have a look at the Laplace transform of this. Now, by definition, the Laplace transform is just the following function. Okay, it's just an improper integral where you multiply through by this exponential, e to the minus st. Okay, well, we're integrating from 0 towards infinity. Now, this step function, it's always 0 up until t equals a. Up until this sort of jump point, right? It's always 0 up until there. So what I can do is split this integral from 0 to a, and then from a to positive infinity, or off to positive infinity. Okay? Now, at the point A, yep. At the point A, the function's a half, and then to the right, it's 1. Now, obviously, this is 0. This is 0 because I'm integrating just over a point. That's got to be 0. So we're just left with this. Okay, well, let's just integrate this. So I hold s constant and I integrate with respect to t. Okay, so as t goes to infinity, this is going to become 0 because s is strictly greater than 0. So this part's going to be 0 for the first limit of integration, and secondly, I can just replace t with a, so I get something like this. And we get the transform. Okay, so that confirms what our table was saying here. Okay. So that's the Laplace transform. What we would like to do, though, is get comfortable with switching these type of switching functions, getting comfortable with their graphs. Okay. Sometimes you'll be given a function, a discontinuous function, and you'll be asked to take the transform of it. Well, that involves, in many cases, writing it using this Heaviside step function. So let's have a look at some examples using the graphs of these functions and showing how to sketch them. All right, here's a couple of functions here. We're asked to sketch their graphs. Okay. Now, I'm going to start doing this sort of stuff I'm going to put in quite a bit of detail for the first few, but after a while, you'll get better, so you won't need to think about all the different cases. So firstly, let's just consider the function g of t. What you can do, it's not a super speedy method, but what you can do is think about where is this 0, where is it 1, and where is it 1/2. Okay, well, for t less than 1, this is 0. So the whole thing is going to be 1 plus 0 for t less than 1. Okay, because this is 0 there. Now at t equals 1, this will be a half. So I'll get 1 plus 1/2. And for t greater than 1, this step function is positive 1. So it's 1 plus 1. So all I need to do now is sketch those parts of the graph separately, and I'm on my way. Okay, so the change happens at 1, t equals 1, sorry. And to the left, it's just 1. At the point t equals 1, it's 1 plus 1/2, which is 3 on 2. And then to the right, it's positive 2. Okay? Now, of course, that's just the Heaviside function u of t minus 1 shifted up the vertical axis 1 unit. Okay, so for the second one, let's do that reasonably carefully as well. All right? So for t less than 2, this is 0. So it's 1 minus 0 for t less than 2. At t equals 2, it's going to be 2 times a half over here, so 1 minus 2 times a half. T equals 2. And for t greater than 2, it's going to be 1 minus 2 times 1. Okay, so you can simplify this and then sketch your graph. So the point of interest is 2. So to the left of 2, it's just 1. At 2, it's 1 minus 1, which is 0. And to the right of 2, it's just minus 1. Okay, so that's like a step down rather than a step up. Questions? Now, it may seem very basic, and I've probably written in too much here, but it's my understanding that students actually underestimate how difficult these things are sometimes. All right, so now it's starting to get a bit harder because you've got two-step functions in the one definition. Sketch the graph of these functions. Okay, so let's just see what's happening. Well, the points of interest are t equals 1 and t equals 2. Okay? For the first one, t equals 1 and t equals 2 are the points of interest. That's where something's going to happen. Something's going to switch on or switch off, something like that. Okay? So what I'm going to do is just break it down, and I won't do this for all of them, is just break it down into the case where t's less than 1, t's between 1 and 2, and when t's greater than 1. Okay? All right. So for t less than 1, what's that going to be? What's the value of that going to be for t less than 1? 0. What about that? It's also 0. Okay, that hasn't switched on yet. That hasn't switched on yet for t less than 1. So it's 0 plus 0. Okay, what about at t equals 1? Well, that'll be a half, and that's still 0. It hasn't switched on yet. Okay, so it's going to be a half plus 0. What about t between 1 and 2? Well, that's switched on, so that'll be 1. That hasn't switched on. That'll still be 0. So it'll be 1 plus 0, 1. What about t equals 2? Well, that's still 1. That's 1 half. So it'll be 3 on 2. Now for t greater than 2, that's still switched on, and that's just switched on. So that's 1 plus 1, 2. So can you see how it's starting to get a little bit harder now? Okay? So if I wanted to sketch the graph of this function, okay, it's 0, so this is 1, this is 2, it's 0 here. It's then 1 half, it's then 1, it's then 3 on 2, and from then on it's positive 2. Okay, so now for part 2, can we sketch it without actually writing down what W is? Well, let's try. Okay. The points of interest, again, are t equals 1 and t equals 2. So to the left, of t equals 1, that's 0 because it hasn't switched on, so's that. So that's what I would get. At t equals 1, that'll be a half, and that's still 0. But for t between 1 and 2, that's still 1. Well, actually, that's 1, right? And that'll be 0 still, right? So it'll be 1 minus 0. Now at t equals 2, this is still 1. This is just a half, so it's 1 minus 2 times a half. 1 minus 1, 0. For t greater than 2, this is still 1, and this is just switched on. So it's 1 minus 2 times 1, minus 1. Okay? Now, some of you will look at that and go, okay, that's easy, I can understand that. But some of you will look at it and go, it's quite hard. Yeah, it can be. Some students struggle with these kinds of representations. Okay, but if you're ever worried, you can always break it down to just the intervals before any jumps, at any jumps, and after any jumps. So we've been looking at step functions, and the idea is to have some sort of compact way of writing discontinuous functions that get switched on and off. Okay, so you may have heard of a square wave, right? Can I have a show of the square wave function? Who's heard of that? Okay, it's the circuit theory. You can, of course, use this Heaviside step function to describe ideas like a square wave. Now, those kinds of graphs have infinite number of jumps, right? So it's a little bit more complex. But we're just starting off simply. Okay, here we're asked to sketch the functions listed here. So let's just concentrate on the first one, and I guess I can write out some of the steps for it. So you'll notice here that I've got the step function multiplied by another function of t, in this case t squared. Okay? Now I've just put the square brackets in so you don't get them confused with u of t minus 1 here. Okay, so that's just, some people sort of see round brackets here and they think it's u times t minus 1 times t squared. No. Okay, so the point of interest for part 1 is t equals 1. That's the point that we're interested in. So for t to the left of 1, this is 0. So 0 times t squared is 0. So it'll be 1 minus 0. At t equals 1, the step function is 1/2. Okay, so it'll be 1 minus 1/2 times a half squared, because t equals a half. T equals 1, right? So at t equals 1, this is a half, so it'll be 1 minus a half times 1 squared. Okay? And to the right of our point of interest, this is now switched on fully, so this is 1, so it's 1 minus 1 times t squared. Okay, so let's put this together and see what we come up with. Okay, so our point of interest is 1. To the left of 1, our graph is just the value of our function's 1. At t equals 1, well, I'm going to get 1 minus a half, which is just here. And then what is this? This is 1 minus t squared. Now, if you look at the graph of 1 minus t squared, it actually cuts the t-axis at this point. So it's a parabola, kind of like an N-shaped parabola. So it'll look something like that. Okay, maybe that's a bit... Actually, let me just fix that up a bit. That's a bit better. Okay. So you can see what's happened, at least in this picture, is that all right? I've got just a constant values here, and then this 1 minus t squared function gets switched on after t equals 1. Okay, now the second part is actually, I've kind of given it away with writing this notation here. Can anyone suggest how we can quickly draw the graph for the second function? Just shift it, right? Just shift g of t 1 unit to the right. Okay, so just take this graph, shift it 1 unit to the right. But what happens if I didn't have that information? I just had that. Well, that's a little bit harder. Okay, so let's pretend that we didn't have that information and we just wanted to look at this. All right, well, the point of interest now is 2. So I don't know, let's call this h of t or something. Okay, so the point of interest is 2 in this case. T equals 2. And if you, say, do a similar analysis as I have up here, you should get something like the following. Okay, now actually this part of the parabola turns out to be this function here. Okay, so if we didn't have this minus 1, we just started with this. You know, you could do this just sort of in a piecewise kind of portrayal, and you'll come up with the following. All right, here's another question. This function is defined in a piecewise manner, and we're asked to write f in terms of the Heaviside step function. Now, before we get to that, I'm actually going to do a simpler one, and we'll come back to this. Okay, so just leave a little bit of room sort of here so you can do the solution to this one. I'm going to actually start with a simpler example. Okay, so I've given a function here, describe f in terms of the unit step function. What I like to do with these particular examples is just draw a graph first and see what happens. Now, notice that this function isn't defined at t equals 1. It's not a big problem. Okay, so I'm going to actually just draw a graph down here. So on this interval, it's 0. And then to the right of t equals 1, it's the linear function t plus 1. Okay, so I guess it's going to look something like that. Okay. Now, the function is not defined at t equals 1, but yet our Heaviside step function is. Now, that's not a big deal. People sort of scratch their heads a bit about that. It's not a big deal. Let me show you. Okay. At this point, nothing's happening, right? It's just 0. Then at t equals, from t equals 1 onwards, or to the right of t equals 1, this function gets switched on. Okay, so how can I do it? Well, something like this. Okay. Actually, I don't even need that bracket there. You can just cover that up and have it like this. Okay, so just cover that bracket up if you want. Okay. So what I've done now is I've actually expressed f as a function which is multiplying through by some Heaviside step function. Okay. Now, if you want to do a little bit of algebra, you can rearrange this, I'm sure, and have a t minus 1 there plus or minus an extra term. But I think that's good enough for now, actually. Okay? Let's just check to make sure it works. Well, for t to the left of 1, this is 0. So it'll be 0 times this, which is exactly what we have here. To the right of 1, this is 1. So 1 times this function gives me t plus 1, which is just that. So this is the one that I kind of reworded. I didn't like the wording down the bottom. So here I've got another function. It's slightly different to the function that we just saw. Why? Because of this otherwise term. So if I wanted to sketch the graph of this function, I'm interested in the interval 0 to 4, and then it's 0 everywhere else, including negative values of t. Okay, it's not defined, oh, it is defined at 4, yep. So that's, you can colour that in. Okay, so the question is, how do I describe that in terms of Heaviside step functions? Well, you can see there's 2 jump points. One's at t equals 0, although it's not strictly speaking a jump, but something switched on there. And then there's another jump point or a switch at t equals 4. So who thinks they can describe that function in terms of Heaviside functions on the whole of the t-axis? Okay, except possibly at t equals 4. Who thinks they can do it? Anyone? Well, let's just consider the first switch. Okay, so forget about this. Let's just worry about this. Okay, so to the left, it's 0, and to the right of 0, it's the function t. So what would our description be just for this part of the graph? Anyone? Not quite, almost, but see, if it was 1 afterwards, it would be, but it's not. It's the function t. Yeah, t times u of t. Okay? Now, what we have to do at this point is switch everything off. And it happens at the point 4. So to counteract that, let's take a term away. Now, that hasn't covered the case when t equals 4, so I guess strictly speaking, you should have this. Okay? Now, it does take a while to get comfortable with these Heaviside functions, okay? So if you're not getting it straight away, don't worry too much. It'll come with practice and really trying to see what's happening with the switching.